Okay. So today's topic is the last section in chapter 7, the root systems. So we learned the definition of root systems of the classical Lie algebras. So we will consider so these four are called the classical Lie algebra. So special linear algebra, SL n plus 1c, and orthogonal algebra, SO 2, and for some reason we will divide orthogonal algebra in two cases when this dimension or this is 2n, index is 2n or 2n plus 1. And symplectic algebra, SP and C. And this special linear algebra, the root system of this is called root system. It's commonly called root system of type AN. And root system of type DN, this is a root system of type BN. This is the root system of type CN. Of course, usually it's listed A, B, C, D, but in this book, it's listed in this way. So, but we will, I'm going to go through rather thoroughly of the root systems of the first two classical types, so type AN and type DN. By the way, this subscript n indicates that the rank of this is n. So the rank, what is the rank of a Lie algebra? So when we have a semi-simple Lie algebra, there is a Cartan subalgebra, and the dimension of the Cartan subalgebra is the rank. So the rank is n. That's why we consider n plus 1, because if you consider n, the rank will be n minus 1. We want the rank to be n, just for this convention. And we will use, so for when you have a Cartan, when you have a semi-simple Lie algebra, we will study these two in the following way. So G is this K complexification, and T is a maximal commutative subalgebra of K, and H Cartan subalgebra can be defined this way: the complexification of this T, and R is the root system, or the root system, meaning term of say G, which means basically the set of all roots. And we know that this Lie algebra can be decomposed into these root spaces, so Cartan subalgebra and these root spaces. So for 1 and 2, we will compute, or we will find these. We will find this compact real form K, and then this maximal commutative subalgebra and Cartan subalgebra. We will find all the roots, and then we will find the root space decomposition. Okay, for type AN and type DN. Then once you've seen this for this P and C, and you can just work out in your own. All right. Oh, and we know that there is an inner product, right? We will use the inner product inner product on H, right? Given by this. So these are all matrices, so we can this trace X adjoint Y trace. Maybe with some constant multiplication, if C can be 1 or 2 or anything, with some constant. Just to normalize so that everything is nice. Okay, so this is what we are going to do today. So far we learned this kind of general theory, so we will really look at concrete examples. Yeah. Okay? So first, G is the special linear group, a linear algebra, like that. So this is, I told you, type AN. First of all, the compact real form we already know. The compact real form. So it's K is SU n plus 1. We know that this is a complexification of this. But what is this? This is a set of all n by n, n plus 1 by n plus 1 matrices, right? So met n plus 1 C, 1 C. Because it's n by n, n plus 1 by n plus 1 matrices, such that, what's that? So special means trace 0, and unitary means this adjoint is minus this, because they came from Lie group. So if you have Lie group corresponding Lie algebra, we have these relations. Okay, so then we have this. So we have compact real form. This is good. Now let's define this K to be the set of diagonal matrices in K. Let's just collect all the diagonal matrices here. So it has to be, everything here has 0 trace and this. Oh, I think, yeah, this is not good. Yeah. You know, it's a real, right? No. Yeah, C. C, right? Sorry about that. But because of this, we know the diagonal entries must be of the form I times real, right? Because, yeah. So it is a real vector space, but yeah, the entries are complex numbers. So what is this? So as a if you want to really look at the matrices, it looks like this. I, A, n plus 1. So diagonal matrices of this form. Each AJ is real, right? And of course, their sum must be 0, because trace 0. Okay? So this is a set of matrices of this form. Okay? And what is H? So H, of course, we define H as the complexification of this. That means exactly the same form, but now 0. So now we can have complex numbers, right? So here is all real but complex, because that's the definition. But then T is a maximal commutative sub-algebra of K. Why? We have to prove it. We'll prove it, but notice that if Okay. So we need to prove it. So let's prove it. Proof. Oh, let's write proposition. If X matrix n plus 1 by n plus 1 with complex entries, if this commutes, if a matrix commutes with H, then X is diagonal. Like this, diagonal matrix. Proof. By the way, it is enough to prove the proposition. Proposition would imply this statement. Because, okay, people proving this, if we accept this proposition at the moment, then we obtain that this is a maximal commutative subalgebra, because if X commute, because maximal commutative subalgebra of K commutes with T, then we want to show that X is in T. Then actually, because H is merely a complexification of this, X also commutes with H, which is just a complexification. But then by the proposition, X is diagonal, right? Oh, diagonal. Maybe we should write K, right? Because maximal commutative subalgebra in K. X is diagonal, but it is in K. That means X is in T, because T is exactly in that form. Diagonal matrix is in T, in K. So if you prove this proposition, then yeah, we are done for this statement. Is this okay? So we will prove the proposition. Okay, how can you prove the proposition? Proof. So suppose that X, let's write this as an entry. The entry is ij entry is X sub ij. Suppose that this commute with H. Just all diagonal, complex diagonal matrices with zero trace. We want to show that diagonal. So we want to show that X is diagonal. So to do that, let's define these elementary matrices for J, K, N. Let, I think it should be N plus 1. E, J, K is a zero matrix with only one non-zero element, or only one in this coordinate JK. It's like that, and then zeros elsewhere. Zeros elsewhere. It's like a 0, 0, 0, etc. Right? So it's obviously these forms are basis of this matrix n plus 1 by n plus 1 space of matrices. All right, and let H, J, K be this matrix E, J, J minus E, K, K. Then it is in H, right? This diagonal matrix, because it's diagonal entry matrix with 1 in J diagonal entry, minus 1 in K diagonal entry, then zeros elsewhere. So it is. So in fact, if J is less than K, these form a basis of this space. So these form a basis of H. So the dimension of H is n. So because it's a diagonal entry, the sum of diagonal entries is 0. Okay, then by this assumption, x commutes with everything. So in particular, x must commute with this. Then we can say that 0 is h, j, k, and x, right? But now let's use the definition of this. Then this is in fact, let me just write down the formula. 2 times x, j, k, e, j, k minus 2 times x, k, j, e, k, j plus other terms. Other terms. Meaning not different from e, j, k, e, k, j. Because they form a basis of space of matrices, right? N plus 1 by n plus 1. You can always write this as sum of these, a linear combination of e, j, k's. And the coefficient for jk, e, j, k is this, kj, the coefficient is this, and for other term we don't really care. We will show this. Actually, it's a claim. Let's say it's a claim. This one is, of course, true. Claim is this part. If the claim is true, what can we say? It has to be 0. This has to be 0 because they form a basis. So every non-diagonal entry will be 0, so you can conclude that X is indeed a diagonal matrix. Okay? So we will prove this claim. But the proof of this claim is really just basic linear algebra. You know, undergraduate student can do this if they know what to do. So first of all, by definition, it is EJJX, EKKX. But we can just compute each of these because that's basically commutator. If you compute the multiplication of these two matrices, it's going to be X, J, L. This is just a complex number. This is a matrix. And if you compute the minus term, it is it's just a simple computation, so I'm not going to show you. You know how to do this. So this means EJJ comma X, the bracket, means this is how I want to interpret. So we have a matrix, n plus 1 by n plus 1 matrix. We have jth column, jth row. Let's look at this part. So basically, we have zeros except jth column and jth row because we only have this and this. So basically, we have entries of x, but we have, because this is going to be minus, we have plus entries here and 0 here, 0, plus, minus, 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 something like that. This is a kind of X matrix. X matrix, but with this kind of, how can I say, coefficient, let me say. So these are zeros. So this means this is plus means xj comma 1, xj comma 2, etc. I'm just writing this, somehow visualizing these in a matrix, okay? Is this okay? You don't have to do this, but this is how I try to understand or visualize this. I think it's nice to really see this. But of course, this is not the only way. I'm just showing you how to do this. So then EKK will be the same, except J is replaced by K. So what is this? So this is going to be this minus the same thing with k column, kth row. So it will look like this. It's jk. Let's say j is less than k. So we have these columns here. You see. Here is all, let's say, plus, plus, and here all minus, minus, right? Then what happens here? I mean, I think this is not correct, because this is this minus something, right? Sorry about that. So it's going to be minus, minus, plus, because this plus minus came from here, right? And this minus plus came from minus of this with k. Okay? So basically, it looks like this. So what is the entry here then? This entry will be xjk 2 times. Because one came from the first part, the other came from the last part. Again, then this part, what is this? Minus 2xkj. We have a bunch of other terms, but we don't care. But that will prove the claim. Where is it? Yeah, right? So that's it. By the claim, we know that this has to be 0, this has to be 0, because these they form a basis, and non-diagonal entries all vanish. So that's the proof of the claim, and that's the proof of the proposition too. So that's the end. X diagonal. All right, so we proved that P is a maximal commutative subalgebra of K. So what else do we need to do? So now let H be an element in this form in H. So it's a diagonal matrix with complex entries, right? This is a Cartan subalgebra. Then H times E, let's compute EJK. Then, it's diagonal matrix, so it's easy to multiply. It's going to be lambda J EJK. And H EKJ, no. EJKH is lambda K EJK. Just simple computation. And because of this, H bracket EJK is this minus this, right? But they are the same. These matrices, they are the same. So it's equal to lambda J minus lambda K EJK. That means this, the same thing, the root vector. So simultaneous eigenvector for this operator, for all H, right? This is arbitrary H for all H in H, where H is in that way. That means this part is simultaneous eigenvector, or in other words, it's a root vector. It's non-zero. Root, for some root that kind of gives us this value. Okay, for some root. We will find what that root is. Or simultaneous eigenvector. That's the same meaning. And now, because we want to find a root that gives us this value, because root, if this corresponds to root with root alpha, then we want this to be alpha comma H. We want to find vector alpha or matrix alpha. But because we want to really work on not the space of matrices, but Cn. We want to work with C and n plus 1 actually. But you can do that because there's a very simple way to identify this. Actually, this should be n plus 1, right? We can easily identify this with C n plus 1, right? Because it's just diagonal matrix. And there is a inner product here. We need to see what that inner product is in this space under this correspondence. That turns out to be just the usual inner product here. Since H or XY, we use, okay, maybe since, let's say, use the inner product, use the inner product given by this. We know that this is a good inner product. And then identify, say, H, x1, dot, 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 Hn plus 1 with this vector, lambda 1, dot, 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 lambda n plus 1 in this obvious identification, okay, 1 to 1, clearly. Now let's see what happens in this inner product in terms of this. Actually it's quite easy. This can be translated into xj bar, yj bar. Oh no, not bar, right? Of course, if we are assuming that x is x1, dot, 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 xn plus 1, y is y1, dot, 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 yn plus 1. This is exactly the same as this, which is the usual or the standard inner product in Cn plus 1. So standard inner product in Cn, so which is good. So now I told you we want to find alpha, a root or vector in Cn plus 1 satisfying this. So we want, say, alpha jk in H. So in this case, it's just a diagonal matrix, but we can think of this as n plus 1 tuple of complex numbers, such that H E j k equals alpha jk H E j k for all H, right? Because that's the definition of a root vector. But what is this? Can you find such? But we want this to be what? This has to be lambda j minus lambda k. For which vector? Now think of this as now element in Cn plus 1. Also this element in Cn plus 1. We want to have inner product so that we can extract jth component minus kth component. How can we find such a vector? Actually, it's just Ej minus Ek. This is the usual, what's that? A standard vector, standard basis vector in Cn plus 1. Because this inner product with H will give us lambda j. And this inner product with H will give us lambda k. So because of minus, we get what we want. So the usual standard, the jth component, standard basis vector. All right? Yeah, so we found a root vector, a root and root vectors. And we know from this root space decomposition of G, we know G is this SL n plus 1 C. This has this decomposition, alpha in R G alpha. But we know that G decomposes into H, which is the space of diagonal matrices, JK, JK, no, I think just J different than K. 1 JK from n plus for all pairs of jk different from 1 to n plus 1, g alpha jk. Why? Because g alpha jk, this means the span of the root vector. What is the span? Do you remember the root vector for this? ejk, span of ejk. This, so basically from here, every matrix can be written as, using these you can kind of give any number to this jk entry. And for the diagonal entries, we have this. So this is really the decomposition. So that means we found all roots. We found all roots. These are all the roots. There are no more than that. Does this make sense? We found all the roots because we have this decomposition. So root R is indeed alpha jk, where jk different, or in other words, because we know that alpha jk is ej minus ek, these are all possible roots. And this is called type A and root system. So type A and root system looks like this. And notice that ei minus ei plus 1 from I1 to n, this is a basis of H. So I told you already, but the rank of SL n plus 1 C is defined to be the dimension of H, which is n. So the rank is n. That's why it's type A n instead of type A n plus 1. Alright, so we found all the root space decomposition. So yeah, we are pretty happy now. We will be even happier because we can find the Weyl group. We can find a complete description of the Weyl group, which is very nice. So to do that, let's look at some geometry of these roots. So note that every root, what is the length of root? This is, inner product square root. Square root of 2, right? Because it's just ej minus ek, so yeah, for all roots. For all, of course, jk different. And what is alpha jk inner product with different alpha jk? Or they might be the same, but always 0 or plus minus 1 or plus minus 2, right? Because we have only 1, 1, and 1 minus 1 in each vector. Okay? Agree? And 2 times this. We know that root system must satisfy this condition. This is always an integer. Right? But this is the length squared, so it will cancel, right? So it's always inside. Okay, then let's see what this is. This can be. So let alpha beta be the root in our type A root system. And suppose that alpha is not a multiple of not a multiple of beta, because it is clear it is it's just opposite or the same. Not, let's assume that they are not. And let's say theta is the angle between alpha beta, right? Like this. I think I should write them with the same length because they are really of same length. So the situation is like that. And what is cosine theta? Do you remember cosine theta in terms of alpha beta? it's been a long time you've seen this, right? It is something like that. And this is going to be 2. So it's alpha comma beta over 2. So this is either 0 plus or minus 1 plus or minus 2. So we know what this angle should be. So we always have this. So theta, depending on this alpha beta, if this is, okay, alpha is not equal to plus or minus 2, that means this is not equal to plus or minus it cannot be plus or minus 1 because cosine because cosine. That means this is 0 or plus or minus 1. It cannot be plus or minus 2 because we assume this. So if this is 0, let's say minus. If this is minus, so let's say plus 1, 0 or minus 1, we have 3 possibilities. In each case, we have theta is going to be pi over 3, pi over 2, 2 pi over 3. So we have only angles. These are only possible angles. Either they are right angle, or this is the right angle. This is like something like this. We always have this. And now let's consider the Weyl group, type AN root system. For simplicity, I'm going to denote S sub sk, S sub jk, which is really S sub alpha jk, because alpha jk is a root. This is, by definition, reflection. The reflection about the hyperplane orthogonal to what? Alpha jk, which is ej minus ek. So this acts on Cn plus 1, the space Cn plus 1. But we can only focus on Rn plus 1 because the roots are always there. Because roots, this is, you can think of this as Rn plus 1. Okay, so let's consider this case. Let's just consider the plane spanned by this Ej and Ek. Right? We have 2 vectors, Ej, Ek, and then we can find the span of these 2 vectors. Now we have a plane. Now what is Ej minus Ek? It looks like this, or something like this. This is minus Ek. It's Ej minus Ek, or if you want, alpha jk. So the reflection about the hyperplane orthogonal to this, that means reflection about, in this plane, about this. And for other vectors, like El or E something else, it will be just orthogonal to this, so it will stay there. That means Sjk, if we apply this to Ej, then what do we get? We reflect Ej about this hyperplane, that will be Ek. So it's going to be Ek. What about Sjk applied to Ek? If you reflect this, it's going to be Ej. What about others? Sjk, El for L different from Jk. It stays just there because it will be orthogonal to this. So this operation acts like this. It permutes the coordinate, jth coordinate, and it switches jth coordinate and kth coordinate, while it doesn't do anything to other coordinate. So that means xjk applied to x1 dot 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 xn plus 1. This is like x1 x. Let's say this is the jth coordinate and kth coordinate. Yes. Something like the only change is something like that. So we can think of this as a permutation of n plus 1 changing j and k. So in fact, the Weyl group of type AN of the root system of type AN is in fact isomorphic to a symmetric group or permutation group on n plus 1 elements. Yeah, because we have n plus 1 elements like that. It acts like that. And then it is a faithful action. So Weyl group is really this permutation group for type AN. Okay, so that's for type AN. Now let's consider type DN. The orthogonal algebra, SO2NC, which is type DN. So let G be this orthogonal algebra, and then we will do basically the same thing. We will find K, this compact real form, and then T, a maximal commutative subalgebra, and then H, and then root space decomposition. Okay, we will do that. And this, by definition, is special orthogonal group. So it's the set of all matrices, 2n by 2n, complex entries, trace 0. Orthogonal means X transpose is minus X. We want to have matrices like that. And we define that first of all, this T is, we know this, we have seen this, is special orthogonal group, which is just real, it's a set of real matrices, 2n by 2n, trace 0, but same condition. X transpose is minus X. Then we know that then G is the complexification of this. This is okay. Let's define T to be the set of block diagonal matrices now. D1 dot 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 Dn, where the jth block diagonal matrix is this 2 by 2 matrix Aj minus Aj, where each Aj is a real number. Let's define T in this way. And then, of course, we define H to be the complexification, which is really the same thing, except we now allow the entry Aj to be complex. Okay, we have to prove that this is a maximal commutative subalgebra, but we will postpone it a little later. We will prove this after developing a little properties of this. And let C1, we will consider this kind of basic 2 by 2 matrices, minus 1, C2 1 minus I minus 1, C3 1 minus I1, C4 1 I minus I1. They form a basis of 2 by 2 complex matrices. That's easy to see. They form a basis for any 2 by 2 matrix can be written as a unique linear combination of this. And we also define for 1 j less than k less than n, 1 less than l less than 4. So l is from 1 to 4, fixed numbers. Let's define x, j, k, l. So we will define this kind of block matrix consisting of 2 by 2 matrices. CL minus CL. There's a block n by n block matrix consisting of 2 by 2 matrices. Okay? So the empty entries are all zeros. Then this is in where? This is in H. Because the transpose is minus and then 0 diagonal. Okay, so why are we doing this? Because it works if you do this. Yeah, I think finding out all this from the scratch, I think is kind of not so easy. But once everything is shown, then checking that this works is not that hard. All right. So proposition, we will show that these are they are root vectors with roots something given. Proposition. The vectors or matrices I wrote, these are root vectors. Here, root vectors really mean just simultaneous eigenvectors. It's no more than that, because we haven't really checked whether T is maximal. We don't know yet. H is a Cartan subalgebra, but we can still talk about simultaneous eigenvectors. So I write root vectors, but this really means simultaneous eigenvectors, okay? You should understand that way. With root means simultaneous eigenvalues, alpha k l, given by, where the indices all from this satisfying these constraints. This. So root vector means this. Alpha j k l h x j k l. So of course we have to specify what this quantity is. Alpha j k l comma h is just, it has to be a number. So we have 4 cases: I a j plus a k, minus I a j plus a k, I a j minus a k, minus I a j minus a k. Depending on the value, if l equals 1, if l equals 2. What is this number? Of course, H is this block diagonal matrix, as shown before. This is in H. dj is like 0 aj. This is exactly what I wrote. So for this H element in the Cartan subalgebra, we have this relation. That means X is a root vector or simultaneous eigenvector. Alpha is a root. Proof. As you can imagine, it's just a basic computation, basic linear algebra matrix computation. It's basic, but let's do that. We will prove only for x, xjk1, L equals 1 case. So let's write c equals c1. So meaning L equals 1 case. Yeah, the other, you can imagine they are basically the same. What do we need to show? We need to show just the relation xh bracket equals, which is xh minus h, x minus xh. We want this to be this eigenvalue. So I, aj. So we know exactly what we need to show. We just need to prove this identity for explicitly given matrices x, h, right? It should be just straightforward. So what is that? d1 dot 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 dk multiplied, what is x? X is like a c and minus c, where it's jk entry, like that. If you compute this, it's just jk, it's a djc minus dkc. It's like that. Can you read that? And similarly, xh is going to be jk. If you compute them all, it's going to be cdk minus cdj. That means hx is this minus this, which is y and minus y, jk, where y, what is y? Y is, of course, this minus this. djc minus cdk. Everything is 2 by 2 matrix. You know how to multiply them. I have to subtract them. The answer will be, of course, this. It's a simple computation. So that means this part, we know this is exactly this times, I think this is k, this. So everything has this factor, so it's like aj plus ak x. And that's the proof. It's just basic computation. Nothing, nothing is difficult. Okay, so we found possible root vectors and possible roots. And they will be roots and root vectors, of course. Okay, we have to develop a little more properties. Note that G we have SO2 and C, right? And every matrix in G, XA in G is of the form, in this form. Diagonal, so 2 by 2 I'm writing in 2 by 2 matrices. Diagonal, and then of course we may have something here and there, but the transpose must be equal to minus. So if we have CJK here, we must have minus CJK for every non-diagonal and 2 by 2 matrix, like that, because it is in SO2 and C. And of course DJ is a diagonal block diagonal matrix. Transpose is minus of itself. The diagonal entries must be all zeros. So it is really of this form. And CJK can be any matrix, any 2 by 2 matrix, right? but this is inside a span of this C1, C2, these basic matrices. That means everything here, every block diagonal matrix, so this is inside H, right? And the other are inside a span of this, or span of X, JK. That means G is the direct sum of H plus for all alpha, G alpha, where of course I'm writing alpha, R is the set of this. One, two, three, four, and of course G alpha means the span of the root vector, which is X, J, K, L. So we found, in fact, all roots and all root vectors. But of course, we still have to prove that H is really a Cartan subalgebra. We haven't checked that. Okay, now we will consider the inner product, because we still need this step to prove that T is a maximal commutative subalgebra. So now, consider the inner product on H, given by xy equals trace, as usual, x adjoint to y, but somehow we will divide it by 2 because it will be nicer later. And consider this matrix again. This is the same one, H, where of course di or dj is the 2 by 2 matrix of this form. Okay? Let's consider H. If you remember, for type A n case, we have Cartan subalgebra. Every element was like a diagonal matrix. So we were able to identify that as an element in Cn+1. Here, we can still do that. It's not a diagonal matrix, but there are n entries. So we can just use these entries to make it as an element in Cn. So we will identify H with a Cn by this. H is in, okay, let's see. This H, for this H, okay, let's say this way. Maybe over here. A1, A2, ... AN, right? We can identify like that. Very good. But for some reason, for some strange reason, not clear right now, we will somehow put I over here. It's okay, we can identify without I, but it will be nicer if you can realize later. Not clear for now, but it will be clear later. Okay? Using this identification, we can regard H, the Cartan subalgebra, as the vector space C to the n. But now let's see what the inner product is under this correspondence. Okay, I think I can write this as a proposition. Under this identification, the inner product, meaning this, on H corresponds to the usual inner product, the standard inner product, which is nice, on Cn. Proof again is just a basic computation. So let's say let X be this A1 block diagonal matrix, AR, AJ is the usual one, and Y, say B1, Bn, block diagonal matrix again, Bj is 0, Bj minus Bj 0. Alright? Now let's see what their inner product is. And what is the inner product in H? This is by definition 1/2 trace X star Y. What is that? So we multiply this star, so X star is star everywhere, and multiply them. So it's really the trace 1/2 trace of the product of this, which is again block diagonal matrix A1 star B1 dot 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 AN star BN. Right? It looks like this. But this one is really summation AJ BJ. Why? Because it is. Just compute it. AJ star BJ is really this star, so 0 AJ. Yeah, I'm not sure I have to do this, but right? Just to make everything clear, you can multiply them, right? If you multiply them, then AJ bar BJ 0 0 AJ bar BJ. So add them, because that's why we divide this by 2, to make this to be really the usual product instead of half of that or 2 of that. So then, this is okay, right? But now we have to check the corresponding elements of X and Y are like A1 dot 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 AN. What is the usual product of their corresponding Bn? We know that it's a complex linear in the first component, linear in the second component, so it's I bar I, A1 dot 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 AN. I think we could just compute it directly, but this is exactly this. So yeah, that's the proof. So inner product, we know exactly what that is in this correspondence, the usual standard inner product. Okay, now we have initially H, but we can kind of move them into Cn, and we found roots in H, so we want to know what they correspond to in this Cn, and they also have nice interpretation or formula as elements in Cn under this correspondence. The roots that we found. The roots are plus minus EJ, plus minus EK, 1 J less than K less than or equal to N. So this really something like alpha IJ L. So let's prove it. Proof is simple. So let's say H corresponds to this A1 dot 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 AN. That means H is a block diagonal matrix, D1, D2, DJ, Dn, and then DJ is 2 by 2 matrix like this over here. Okay. And the root, we know the roots are this A, J, K, L, right? L 1 up to 4. These satisfy this K, JK. J, K, L, H. Depending on L, we have several four types of numbers, but they are all, in fact, of this form. AJ. As for L, 1, 2, 3, 4, if you compute them, then it looks like that. But what is this then? Alpha j, k, l. So here, this is like I, a1, dot, 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 an. For which vector do we have this property? These are them. Correspond to plus minus ej, plus minus ek. Because we want to extract the jth component and kth component. And I is here, right? And we put I at the beginning because we want the root correspond to this without I. If we used here without, if you don't consider this, then we have to say root correspond to I times something. So, but we don't really want that. So that's why we put I at the beginning. So that's it. So the root of this form. Just type B. This is a type Dn root system. So R is really in Rn, not Cn. I mean, it is in Cn, but yes, in particular, it is in Rn, because this is everything is real. Okay, finally, now we can prove that T is the maximal commutative subalgebra using the theory that we developed here. So recall that T is this block diagonal matrices dj 0, aj, minus aj, 0, but each aj is a real number. And K is SO2n, special orthogonal real matrices. Proposition T is a maximal commutative subalgebra of K. If you prove this, then everything is done. Then H is really a Cartan subalgebra, A alphas are really the roots, and X, J, K, L, they are really the root vectors, and everything is done. Okay, so to prove this, we assume that suppose that X is in K, commutes, suppose that it commutes with T. Then, of course, then X commutes with H, because H is just a complexification. So it also commutes with the H, the algebra we defined. And we already proved that, so X is in K, but K is in G, of course. G is the complexification of this. And we know that G decomposes into this. Yeah, we proved this without, we really didn't really use the fact that H is a Cartan subalgebra, R is a root. We mentioned that R is just called R root, but really R is just a simultaneous eigenvector, eigenvalues, and these are just simultaneous eigenspaces, etc., etc. So, as a vector space, everything is completely fine. So we can write X as a linear sum uniquely as a linear sum like this. H0 is in H, of course. C alpha, X alpha. Of course, X alpha is in G alpha. We can write in this way. And now, since X commutes with H, for all H in H, we have what? 0 is equal to Hx, right? But let's expand X using this formula. H comma H0 plus summation alpha for all alpha in the root alpha H X alpha. Okay? But x alpha is in G alpha means it is root or eigenvector for the H adjoint map. So, but this is 0. H is diagonal matrices, so they always commute each other. C alpha, and then we can rewrite this as a alpha comma H x alpha. But now we expressed 0 as a linear combination of x alphas, but x alphas, so this is a direct sum, a vector space direct sum. So this has to be 0. The coefficient must be 0. So C alpha is 0 for all alpha in the root or R, or for all H in the Cartan subalgebra, or H. But alpha is we know that there exists, or we don't really have to say that. Just take alpha. Alpha is also an element in H. Just C alpha, alpha comma alpha is 0, right? But of course, then that means C alpha is 0. Because alpha is in H. That means there's nothing here. So X is really H0, which is in H. But now X was in K. So let me finish over here. Then X is in H intersect K, which is exactly T. So that's the proof. So T is maximal commutative. Okay, so we did it for type A, type D, and there are two more things, type C and type B. They are all written in the textbook, so you can just read the textbook. But let me just tell you the answer or the result. This is type Pn. In this case, root system is EJ, EK, 1J. This is type Dn root system, right? This is type Dn, but we have more. Plus minus EJ. This is the root system of type Bn. And if G is SP and C, and this is called type Cn, and the root system is pretty much the same D and type Dn root system. Union, almost the same, except we have 2 times EJ, like that. Oh yeah, so this is the end of section 7, and next week we will start a new chapter called the root system. And we will define, we already defined root system just in terms of vectors and some axioms. So we can kind of forget about all the semi-simple Lie algebra, and then we can just study root system just by using the definition or axioms. So yeah, hopefully if you had difficulties in chapter 7, it will be a reset for you. So hopefully next week will be more understandable if it was not for this week. Okay, thank you for your attention. I'll see you next time.